When I was trying to decide what to discuss today, there's a lot of different things I do in my lab, and I was considering. I gave a talk at the Reinforcement Learning Conference in Amherst not too long ago. That was sort of my sort of retrospective of all of the reinforcement learning research that has gone, especially from my group, but throughout the community over the last 30 years, and I sort of divided into themes. And I was thinking of repeating that here. But decided not to for two reasons. One, because I think several people here were already at that talk. It's also online, so I encourage you to look at it. And also, there's a shorter time span here. So instead, what I decided to do is focus in on multi-agent reinforcement learning. And I'm going to talk mainly about two pieces of work. One that focuses on cooperative multi-agent setting, and one that's a more competitive multi-agent setting. I do a bunch of robotics in my lab as well, and so just as a quick teaser, because I know John's talk is next, is going to be focusing on robotics. I just wanted to say a little bit about some work that I'm doing collaboratively with UK and then Yifeng Zhu, who's on the job market this year, on vision-based manipulation from single human videos with sort of an object-centric representation. And I'm not going to give that talk. I'm just going to show you sort of the punchline video from it, which is where there's a single human demonstration that defines a task, and then a robot is able to imitate that where there's different scenes and spatial layouts. And why did that not keep playing? We'll just see here. So different scenes and spatial layouts, different camera angles. The point is that rather than trying to take lots and lots of data to be able to learn motion primitives, instead it's taking a single human demonstration and trying to milk as much as possible out of that. So in this case, it's able to work with different camera angles, different lighting conditions. This is a more complex task where the task is to take two items and put them into the boat, and again showing them that the robot's able to mimic this. To work in extreme lighting conditions, and so this is all sort of from the perspective of and it has already been said in this workshop as well, that if you're in the real world, you're not going to be able to I don't think, and as Michael said and as others have said, you're not going to be able to do everything from scratch. Here it's showing that it can work. The demonstration can be with one mug, and it can still work with other items of the same class because it does take a little language input. It turns that the task is about moving the mug. So I'm not telling the details there. It's just a teaser, but if you're interested, look for Yifeng's work. Okay, so to the main event, multi-agent reinforcement learning. First, I am coming from UT Austin. We've been really fortunate to have one of the first NSF AI institutes, the one on foundations of machine learning, that's led by Adam Clivens. And Sham's been a part of that as well. We have a great ethical AI initiative that I've been a part of, both outside of UT, the AI 100 study, and then Good Systems at UT. And I'm serving as director of Texas Robotics, and just wanted to say we have a beautiful new space that used to be a gymnasium. It's now filled with robots. This was showing before it. I hope many of you are going to be able to come and see it. And a fantastic group of robotics faculty across 4 different departments. But my research question, and the thing that's going to inspire this talk, that I've been looking at for the past 3 decades or so, is to what degree can autonomous intelligence agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so this really is about reinforcement learning and about multi-agent systems, and sort of, full cooperation is one extreme, competition is the other extreme. There's also intermediate cases as well, but I'm going to look at those extremes. And in line with the sort of fantastic panel on bridging theory and practice, I've sort of tried to bridge that in my lab itself. I have some sort of what I call bottom-up, more theoretical and algorithmic kind of work, but I've also been inspired by a bunch of more use cases, and including robot soccer and general purpose service robots, autonomous driving, and so I'll talk about some of those today as well. But my journey into right, and so the outline is going to be that I'm going to start by talking about a cooperative, sort of a cooperative version of Multiagent RL, and then talk about GT Sophie, my work at Sony with a large team of people on a very competitive scenario. So, but my journey into multi-agent reinforcement learning really started many years ago. This is my favorite picture of Rich, where he said he's laser focused on sort of general purpose intelligence. But we had a paper back at ICML around 25 years ago. With the work started when we were both at AT&T, and it was in a both competitive and cooperative scenario in robot soccer, but we were just learning the red agents. It was we sort of formulated this game of robot soccer keep away, where the red agents had to learn through reinforcement learning. They were using independent sarsa lambda, each agent learning by itself what to do, and over about a day of experience, they learned a very effective control policy. I'm not showing the full results here, but it did much better than a hand-coded policy and a random policy. The biggest lesson that came out of that from a paper in adaptive behavior, which was I think the original paper was at ICML 2021, but in 2003 we analyzed what's the difference if we just learn one of those keepers and the other two are fixed. It's actually quite an easy learning problem. It's essentially a single agent problem, because everything there's only one agent in your control. Everything else, nothing else is changing. But as soon as you move to two agents learning at the same time, now it's non-stationary. One can learn, the other one responds, and it's just as hard as having three learning, right? There's a big step between a single agent problem and a multi-agent problem, and then there's some other work that came out of my lab that was Doran Chakraborty looked at some very theoretical multi-agent learning work that I think was way ahead of its time, but an algorithm that he called Seamless for convergence with model learning and safety, which was the first multi-agent learning algorithm that achieves convergence to Nash equilibrium in self-play, exhibited targeted optimality, which means that it converges to the best response against memory-bounded counterparts, and also never did worse than Minimax. And I think there were pack convergence guarantees, very nicely analyzed. I think this is work that we could come back and revisit now. But what I've been really focused on a lot in the last almost more than a decade now is this problem that I'm going to focus on here called ad hoc teamwork. And so. And in particular, I'm going to present a paper that just appeared at NeurIPS about a month ago. The first author is Caroline Wang. She's a PhD student in my lab right now, but it's joint work with several other people as well. And it's introducing a new problem in a first approach that's a generalization of the ad hoc teamwork problem called N-agent ad hoc teamwork. So what's the scenario here? First of all, the motivation is that as I've already sort of motivated, there's not just individual agents in the world. If that I have to interact with other agents, they're going to respond to me. I'm going to respond to them. This comes up in traffic. This can come up in multi-robot, multiple robots in warehouses. It's just sort of, to me, it's a fact of life that we live in a multi-agent world, and so the initial approaches to this kind of to this reality were to think about, okay, let's create some coordination algorithms or mechanisms for agents to work together. And so people, back in the 1990s or so, maybe even a little earlier, were thinking about ways to do pre-coordinated teamwork, where an expert provides agents with coordination mechanisms, conventions, role assignments, communication protocols, or agents could, as in that keep away research I showed, agents could learn and establish those conventions by interacting with each other for an extensive period of time. The idea of ad hoc teamwork is that often we have to coordinate with other agents who we've never seen before, right? So I play soccer. I can go to another country with people I don't even speak the same language with, I've never seen with before. I can jump on a field and play with them immediately, and or if there's an accident on the road and there's a lot of bystanders, people who've never seen each other before can immediately coordinate so that someone calls 911, someone directs traffic, somebody goes and helps the victims. This is a problem that people are really good at, but had not really been examined at all for autonomous agents. So the goal here was you're controlling a single agent, but you have a team where you're trying to maximize the team's returns, with the idea that teammates are using this unknown policy, and you can't control them. You can't say, oh, the way I'm going to do better is by changing the way my teammates behave. It's got to be, I have to respond to the fact that they're suboptimal. So these are sort of two extremes. There's the fully cooperative setting where you get to set the conventions or learn all together for a long time, or there's the ad hoc, single agent that has to work with all of its teammates. So this is sort of our diagram of the cooperative, the traditional cooperative setting. This is our diagram for the sort of extreme ad hoc or zero-shot communication setting. But in this paper, we sort of generalize to a more intermediate case. What if you have control over a subset of the agents? They get to work together to sort of figure out how they're going to be a good sub-team, but then they're going to have to cooperate with unknown teammates. So if I take that soccer example again, it's like, I have a couple friends that I've played with my whole life. There's 2 or 3 of us, but now we're going to go join a team with 7 or 8 other people. How can we be good, not just as individuals, but as a subgroup? And so that defines, the original ad hoc teamwork problem statement from 15 years ago was, the goal was to create an autonomous agent that's able to efficiently and robustly collaborate with previously unknown teammates on tasks to which they are all individually capable of contributing as team members. So the N-agent ad hoc teamwork problem is almost the same, but now we're going to try to create a set of autonomous agents that have to do the same thing. And so we formalize this as a DEC-POM-DP. Sort of all of the standard components of a DEC-POM-DP is as shown here. But then in addition, there's sort of the way that the team is sampled or formed. There's a set of controlled agents that are sampled, a set of uncontrolled agents, and then sort of the number. So you don't even know how many of you are going to be on the team together. And so, just the thing we're trying to do is come up with a policy for the controlled agents. That's the only thing we have control over. That's me and my teammates. So those are parameterized by theta, and we're trying to find the optimal theta that gives them the best performance when they're paired with random uncontrolled agents from some set, and with this team sampling procedure that will pick some controlled agents, some uncontrolled agents, and then you have to do best as well as you can in expectation. So that's the problem setting that we introduce in this paper, and so the main challenges here we have to generalize. We have to coordinate with non-controlled and potentially unknown teammates, and it's also open in the sense that there could be an unknown number of controlled and uncontrolled teammates. So the paper from NeurIPS starts with a little bit of theoretical analysis. We establish with an existence proof in a toy domain that it is suboptimal to just apply ad hoc teamwork algorithms to the N-agent ad hoc teamwork problem, meaning that the controlled agents can't just all do the same thing. So you can't take one and say, here's an optimal ad hoc teamwork agent, replicate it 3 times, and it's doing as well as it can. There's cases where this sub-team, each of the agents has to do something different. Okay, so that sort of establishes that there's need for specialized algorithms for this problem setting. So when I was trying to decide what to discuss today, there's a lot for this problem setting. And so the main thing I'm going to tell you about here, fairly briefly, hopefully to get you to read the paper in detail, is an algorithm called POM for policy optimization with agent modeling, that has 3 key ideas. That it does do teammate modeling, both the controlled and uncontrolled agents, using a encoder-decoder architecture. I'll have a slide on how that works in a second. It uses independent PPO with parameter sharing for the controlled agents, and then it trains a critic in a actor-critic kind of setting with data from both the controlled and the uncontrolled agents at training time, even though at test time, at deployment time, you don't get any information about those uncontrolled agents. And so I have now one slide on each of these three bullet points. So first, the teammate modeling. It's basically encouraging the agents to be able to take the full history of observations and actions that this agent has taken, and use that to predict the next observations and actions of the teammates, both the controlled and the uncontrolled teammates. So basically trying to learn a latent representation that is sufficient to encode from your history of observations what types of teammates you're interacting with now in this episode. Okay, and so that's the thing that's going to allow the agent to customize its behavior based on the team it's currently on. And then from that latent representation, it's going to learn both the policy network and a value network. Then the policy optimization itself takes that latent representation, and it's just using straightforward PPO with the agents during training time, each sort of learning from their own experience, but with full parameter sharing, so that an update from one controlled agent is basically all of their experience is pooled into a single set of weights, and it controls all of the controlled agents, but because they have different observations, they're able to do different things, right? They're in different states themselves, and then so it allows them to coordinate as a sub-team. And then finally, like I said, they train both the actor and the critic. Well, the critic is trained from both the controlled and uncontrolled teammates' data, both their observations and actions. So it's trying to predict both of those. The actor, which is what you really need at deployment time, has to condition only on its the observations and the data of the controlled teammates. And so when you put it all together, you get back to this diagram that I showed you before, an algorithm for n-agent ad hoc teamwork. And I think I don't think it's the best you can do for this domain. In fact, we're looking at some improvements right now. But I think it's the first approach to this, I think, quite interesting novel problem. So some of the experiments with POEM, we looked in some in StarCraft and a multi-agent particle environment. We looked at uncontrolled teammate types that were created by a bunch of different multi-agent reinforcement learning algorithms, but where there were different seeds, and each type was divided into training sets and test sets, so that at test time you were coordinating with agents that you didn't get to train with. That's what makes it ad hoc teamwork. They're out of distribution to some extent. And then we compared against 3 baselines. So we looked at what happens if we just do independent PPO with no agent modeling, none of that latent representation or anything. What if we do just that ablation where the team doesn't get to do anything unified, but you just have individual agents and then put them together at deployment time? And then we also looked at each of these algorithms trained in self-play. And what we found is, this is the sort of the main result. This was in Predator-Prey. The red star is how well you can POEM or IPPO with without the agent modeling would do if they're training, if they're tested with the same agents they were trained with. But then the real result we care about is when they're tested with agents that were trained with different seeds, and we see that POEM is doing much better in all of these cases than when we don't have this agent modeling. And these same results were similar qualitative results were in StarCraft as well. One of the things that we did is we did identify that it does matter, this out of distribution thing where you train test with agents that you didn't train with does make a big difference. This is what happens if you play agents that they were trained with versus if they play against ones that were trained with a different random seed. And performance degrades significantly for the mismatched agents. So that shows that this out of distribution aspect does create a challenge. We looked at the sample efficiency of learning and found that using POEM does better. Again, the agent modeling makes a difference, a significant difference across all the different domains. We did also, this is an ablation where we took out the training from the uncontrolled agents, and we said, let's just train with the data from the controlled agents. And in both pairs, the blue is better than the orange, the green's better than the red, meaning that this sort of training from uncontrolled agents did make a significant difference. And we also have some results showing that the prediction accuracy of both our observations and the actions, the models we have of our teammates, those improve over time with training. So again, I'm going through this rather quickly, but I hope I encourage you to look at the paper for the full details. Again, this is work led by Caroline and with several other people. And again, the main thing I'd love to get is more people looking at this problem of N-agent ad hoc teamwork and try to beat home, do better. I think there's definitely room for improvement. Okay, so that's sort of the first of the two things I wanted to talk about in detail. But now I'm going to shift gears from cooperation to the competitive setting. So I said I was going to talk about the fully cooperative setting. That's the N-agent ad hoc teamwork. And now I'm going to talk about the fully competitive setting, which is GT Sophie. So this is work with a large group of people at Sony AI. So these are the pictures of the authors. In fact, Tom, who's here in the audience, is going to give a lightning talk later this afternoon that's going to talk about some of the work beyond what I talk about here today. But it's almost 3 years ago now that we published sort of the main result of this work on the cover of Nature in February of 2022. In this talk, all of the videos that I'm going to show you, the white cars are driven by people, and the colored cars are driven by our agent, GT Sophie. And the main punchline was that on what I would claim is a real-world domain. It is a game. It's in a simulator, but Michael talked about his real-life reinforcement learning. His definition, I believe, from that time was that it works on a problem that somebody else created, that it wasn't a problem from the reinforcement learning community like Mountain Car or Taxi or something like that, but it's a problem that other people care about. And this is a problem that other people care about. There's people who've put in their 10,000 hours to become really good at driving in this game. There's sort of international competitions, and we were able to I wasn't sure it was going to be possible when we set out to do it, but we were able to beat the very best at this game. And sort of I think of it in that series of beating humans at something that at chess or Go or poker or Jeopardy. This was the first time it was done in a real-time control task. And the success relied on a great compute architecture, lots of data, top-notch engineering, and a few algorithmic and methodological insights. And this is that lesson again. Let's not throw out everything we know. Let's use our reinforcement learning for the hard bits. Just to give you a sense of this simulator, in case you haven't played before, this video shows on top and bottom Ken Chan, a driver. A very good driver driving both in the real world, as you see on bottom, and driving the same car on the same track in the GT Gran Turismo simulator. And he finished the lap. He was doing his best in both cases, and the lap ended within 1/10 of a second in the simulator from the time that it took him in the real world. So this sort of goes to show just how detailed the model's air resistance and tire friction and weather patterns and everything. So like I said, the punchline event was where this was during COVID, so we were restricted to taking the people from the same country. It was hard to travel around the world at the time, but it turns out that 4 of the very best drivers in Gran Turismo were from Japan. They're shown here, and raced them in 3 car track combinations. These are real, real car track combinations that happen in Formula One racing. Because I'm often asked, in this case, we did train a separate policy for each car track combination. Just like people go out and practice on the track over and over again, we also allowed our RL agent to do that. And I wouldn't be here if this weren't the case, but really the approach was an end-to-end reinforcement learning approach. And And I think the conventional wisdom when we started this out was that this was going to be a problem for model predictive control. That the thing to do was going to be first come up with a line, a path to follow on the track, and then use model predictive control to follow that as closely as possible. And that's not what we did. We really literally did end-to-end deep reinforcement learning starting from random behavior, where the car starts by going backwards or running off the track, running into walls, and in the end is able to get to superhuman performance. The main three challenges, and this is an abbreviated version of the talk, so I can't go into full detail on everything, but the main three challenges are first, race car control. Again, I said it's a real-time control problem, so there's no discrete states, there's not time to think between actions. You have to send out actions at 10 hertz, and it's you're sort of right on the razor edge of control. If you go a little faster, you're going to spin out. A little slower, the opponents can beat you. So that's one problem. That's just if you're racing on an empty track. But the thing that makes it really competitive is that you have to be, there has to be tactics. There's other cars on the road. You have to figure out when to pass, when to block. There's a lot of strategy, the multi-agent competition aspect. And built in is this sort of ill-defined etiquette that if you know something about car racing, that you need to sort of build into the agents to train them to be able to deal with the fact that they're going to get penalized if they do something unsportsmanlike. But there's no well-defined definition of what unsportsmanlike. It's human judgment. So we had to figure out how to bake that in to the agents. To the agents as well. So as I said, it's with end-to-end reinforcement learning. Just to give you a sense of the action space, it's a two-dimensional continuous action space. One dimension for brake or throttle, one dimension for turn left, turn right. The initial rewards when you're on an empty track are just incremental progress along the course, and then we added some penalties for tire slip and going off course and hitting a wall. I'll talk about what happens when it is the multi-agent setting as well. The state space in the Nature paper was not from vision. It was a bunch of sort of the kinds of state variables that a human driver can estimate, velocity and acceleration, the roll, pitch, and yaw, sort of location along the track, things like that. Since then, we have published a paper that does this same task from vision, and sort of going from the pixels. And so that is as possible as the features as well. But in the Nature paper, it was not that. I'm going to skip this slide. There was a computing, to do this, there was, again, there was a lot of engineering that went behind it as well. We partnered with Sony Interactive Entertainment, which is the PlayStation group, to build a huge RL training platform with thousands of cloud-based PlayStations, and used sort of an actor-critic kind of setting with rollout workers creating the experience, a carefully curated experience replay buffer, and then a new algorithm that we developed, which I'll talk about in a second. But that's fundamentally a distributional RL actor-critic kind of algorithm, and this done offline. But then eventually everything gets downloaded onto the PlayStation, and the trained policy is not in the cloud; it's there on the device. So we also had to distill it down to fit on the computing infrastructure people have in their homes. For the algorithm that made the sort of that was the secret sauce, or that made went from reasonable results to superhuman results, was an algorithm we call quantile regression soft actor critic. I think in this room you can probably imagine what that means if you haven't already seen it, but it's basically learning a distributional reward function. So not just what the expected value of an action is, but what's the likelihood that it'll lead to a disastrous value or a really good value. We do use n-step returns and found a sweet spot of around 5-step returns. I do have another slide that goes into a little more detail on QRSAC. I sometimes skip, but this audience, I think it's fine to show. So it is using, trying to minimize the overestimation bias by learning two different Q functions. It's using a Huber loss function on each of the buckets, and the distribution is bucketed into 32 quantiles. And then the neural network training architecture, it's 4 layers deep. this was, I think we've expanded this a little bit. Tom can nod if this is the case. We've gone a little wider, I think. Yeah. In the more recent, no, we do not upgrade my computer now. Okay. But roughly, yeah, there's well, you can see the details here, and dropout of 0.1, mini batch size of 1,024. Learning rates where it's twice as high for the actor than the critic. But then how did it work? So here's what it looks like after 1 hour of learning on an empty track. The car's sort of wobbling around, not doing very well. After 4 hours, after 8 hours, or approximately a week of training, and this, after this week of training, it is as well as people can do. It's like clipping the track, optimally. And getting finding both the best line and when to accelerate and decelerate. So that's the empty track case. We did look at sort of how well it does compared to people. So these are sort of the 100 best times of people on on Kudos Prime, where people sort of register their best lap scores. After 4 hours, it's not really in distribution. After 24 hours of training, only a few people are better than it, even with their very best times. This is showing the distribution of a trained GT Sophie versus the top 5 control times on one of those track car combinations, and on the other one, on the other two, it's way to the left, like beating people by a significant margin. So I did say that just going fast on an empty track isn't enough. We also have to deal with the multi-agent aspect of it. So we do have a competitive, we augment the state space with the relative position and velocity of the other cars around us. We augment the reward function to give a reward for passing, negative reward for being passed. Fairly straightforward. But then another key aspect that we had to learn from practically here was the how do we curate that experience replay buffer? So we needed to create situations for the car to when it was behind one car or behind two or in a pack, also when it was on an empty track. We had to create sort of opportunities for it to learn skills like slipstream passes, where you get in the air resistance of the car in front of you and then sort of bounce out and you use your momentum to pass them, and crossover passes. And so we sort of, we used, this was actually a key technique that made things work, is we used stratified sampling from the buffer to make sure that the right mix of experience was there for every different part of the track. We did this manually at first, and then since then we've worked on automated methods of coming up with how do we get the right mix of experience into the replay buffer for efficient training. So just some quick examples. This is the example of that slipstream pass where the GT Sophie car in color is behind the human-driven car, and then it's using the momentum it can get from being in the lower air resistance, sort of like bicyclists do when they're drafting. So that was a skill that it learned. There's also examples of it. Unfortunately, the sound's not working here, so you sort of hear the commentators saying what's happening. But here's a GT Sophie car sort of making sure that the people don't have a good, easy way to pass it. Again, it's learned that by itself. And then one of my favorites is this crossover pass, where there's two GT Sophie cars that sort of are losing ground to the human-driven cars, and then they come out of the turn, but they get into a position where they can come out of the turn ahead. And in this race, they never looked back after that. So, and then finally, there's this aspect of etiquette. There's this subtle but imprecise sportsmanship rules where you can't do things, you can't cause an avoidable collision or force a driver off the track. You can't do things that are illegitimate. What does that mean? So we had, and if the car was too timid, you can imagine that, like here it has a lead. This was in the first race we did against people, and the people actually beat the GT Sophie agents. And we realized that in this case, it had the announcer was saying, "Oh, there's no way the person's going to catch up." But then it turned out that GT Sophie put on the brakes because it was worried about a collision, and the person was able to pass. But on the other hand, if it's too aggressive, you can imagine also what would happen. This is something, here you can see the setup where the person's driving, but here GT Sophie is pushing the person off the track, and that's not allowed. That gets penalized. So how do we balance that? We augmented the reward function with sort of penalties for collisions that we tried to operationalize what those would be, put those into the reward function. This was something we had to tune with some experience. I guess in the interest of time, I'm not going to, there is also the problem of we got to compete against people once, but we had got to train a whole bunch of policies. How do you pick which policy to sort of put on that stage? That was actually quite an interesting challenge that's covered in the Nature article. But in the end, we had 2 different competitions against these expert human drivers. It was set up so it was 4 people against 4 GT Sophie agents, but the GT Sophie agents were independent. They couldn't work as a team. They had to each work individually. They weren't even aware of whether the cars on the road were other GT Sophies or human-driven. The humans were instructed not to collude. It's not clear to what extent they did or not, but it was set up that you got 10 points for finishing first in the race, 8 for second, 6, 5, 4, 3, 2, 1 afterwards. And Sartre was one of the races was double because it was the harder one. It's where the 24-hour Le Mans happens at Cirque de la Sarthe. The people did beat GT Sophie in July, so of course we asked for a rematch. We went back to the drawing board, fixed some things. I don't have time again in this talk again to go into all of the details. We found that, like I said, there were times when the car gave way unnecessarily. It lost some positions in the start, lost control a couple times. So we improved those things, and in the second race, which happened in October, we were able to finish first and second in each of the races, outperforming the people 104 to 52 by that point scheme that I just showed you. So that did go onto the cover of Nature. Since then, there's a bunch of drivers who have played against it. Since I don't have volume and not much time, I'm not going to play the video here. But I'm not going to leave it run. But people have said that they're learning things by watching the agent. They're learning things by competing against the agent. They're improving and changing their techniques. Emily Jones here says, "Oh, that was I saw something and I said maybe I should try doing that." But one of the key things then is we've deployed this in the game itself. So there's hundreds of thousands of people around the world interacting with GT Sophie. We don't play put it at full strength because that wouldn't be very fun. So we went into sort of how can we make this fun for the game for people playing. We've gotten tons of feedback. I think it's one of the biggest commercial deployments of a reinforcement learning agent ever. Tom is going to talk a little bit about the production challenge. So I'll just say one of the things we've been thinking about is how can we have the agent drive with style. So here we put up a little extra reward for drifting, and the car learned to turn corners like this, which was, I think, sort of a neat thing to see. But it's not done. There's still interesting reinforcement learning challenges upcoming in the game. So as I said, this is not just my work. It's a large team of people at Sony who've been doing this. I apologize for rushing through it, but there's details on our in the Nature article, and then also several follow-up papers since then. And it's been a lot of fun. So so with that, that's I talked a little bit about the fully cooperative multi-agent setting, the N-agent ad hoc teamwork problem. I closed with the fully competitive GT Sophie setting, and that's what I wanted to tell you about Multiagent RL. So thank you.